Thank you, and so I'm glad to be here and to see all of these faces for people that I have been working on their papers for long, and I see them for the first time. I'm going to speak about hydrodynamic behavior of two-species TASEP. So this work that I did during my PhD with my supervisor Luigi Cantini in Laboratoire de Physique Théorique et Modélisation in CY Sergi Paris University. So first, I'll start with a very brief reminder of the most classical result of single-species TASEP that I'm sure most of you know perfectly, but still it's relevant to the following of the speech. Then I'll speak a little bit about this multispecies generalization, and at the end I will just take one single particle of second class, and then I will study the effect of this particle and compare it to some limits of the model with infinite number of particles. Okay, so as I said, like you all know, what is ASEP. So you have particles like move as random walkers with constraints that you have. Each side can on the lattice can host at maximum one particle. So you can have like totally asymmetric when all the particles hovering in the same direction, and symmetric symbol exclusion process when P equals Q. So what's worth mentioning here is that this model or similar models are still like relevant for application. For instance, like I talked with people who are working on active matter, and they study the movement of protein on the filament, Kinsen protein, and molecular motors in general. And they use like they still use this model or a bit more complicated models. So that's part of the motivation why I'm interested in this multispecies generalization. But as well, of course, there is a huge amount of theoretical motivation, because this model has been central for many communities, like stochastical process, out of equilibrium statistical physics, and integrability, as we saw yesterday in the talk of Riemann. So probably the most elementary information about this model is that Bernoulli uniform product is invariant under the dynamic of TASEP, for instance. This has been shown in the seminal paper of Spitzer. So which means that the mean field current is exact. Okay, so we'll see like soon that in the multispecies generalization, like this uniform product measure is not anymore valid, and makes the expression of the current much more complicated. So yeah, if you use like for this like this current, also you can recover the if you write the conservation law for this current, you get like the Burger's equation. And this, like, of course, because this is like a physicist way of describing the situation. You consider constant grain density, and you recover. But of course, there is like very rigorous mathematical way to do it, like using Euler scaling. So yeah, but like this Burger's equation, you can understand just intuitively the evolution of like whatever initial profile. Using this this equation. For instance, like if you have initial profile that's like that's increasing, then the upper part will move at a characteristic speed, which is lower than the lower part, which means that this like increasing part will get steeper and steeper till there'll be a shock. We know that like conservation laws have like shock as solutions, while the other like part of the profile, it will just get less steady, so it'll eventually become a refraction fan. So probably the most like studied like initial condition is this step initial condition, and then you see solve the Burger's equation for this initial condition. Then you get simply like linear profile. So if you compress the system by the space by the time, then you just have a limit shape, which is just a segment. And this is, of course, has been rigorously proved by Ross. You can state it in a rigorous way. So, and not only this is not, of of course not has only proved for this initial condition, but for that's I think for any initial condition with maybe it has to maybe but some like anyway very wide class of initial condition. Okay, so now why are we interested in the multi-species generalization? Because simply let's say if we are speaking about application in traffic flow, then it's very relevant then to have different kinds of particles different kinds of particles. Each, like let's say here the black and the red they exchange with the rate tau black red. Okay, so if you just like put the model like that, is try let's say to solve it. In general, it's not solvable, at least not in the Young-Baxter sense. So if we just like let's say impose Young-Baxter integrability, then we need some restrictions on the rates. So there is in general like two families of models that you can solve with integrability. Like one of them is hierarchical, like totally TASEP, which means that you assume that there is a first class particle that they jump over all of the other particles. Second class particles they jump on the lower like classes, and so there is a hierarchy, and you can, and then still like you still like even with this like structure you need still some restrictions, except if you have just two species, then you can just, if you have two species, then you can just like leave the rates, let's say, arbitrary. So this is the first class particle jumping on in the black. First they jump on the void. So with rate 1, they jump on the second class particle with arbitrary rate beta. And second class particle jump on the void with arbitrary rate alpha. Okay, there is another class of integrable multi-species, which is like ASYMmetric, which is like all particles in one direction. Let's say if you label the species with integers, then in one direction they all jump with one rate, and the second direction jump a different rate. Okay, so but here like we have more parameter, more free parameter in a sense. So okay, this if we just have a single second class particle of with unity rate, this has been introduced almost since TASEP. So this has been so many interesting properties. For instance, it follows the movement of the characteristics, and if you put it like in an initial profile, initial step, initial condition, then it will have a deterministic speed that is drawn from a uniform distribution, as was shown by Ferrari and Kipnis. So then now, if like let's say if we give this second class particle arbitrary rates, so this maybe should be called like a defect or generalized second class particle. So not for, but yeah, I still like do an abusive language and they call it second class particle. So this has still introduced by Malik and Derrida, and they for instance they put it in a ring. They found the stationary measure using matrix exposures and zats, and even like the diffusion constant using beta and zats. This was done by Derrida. Okay, now if you put arbitrary number of defects on the periodic boundary condition, then using integrability you can calculate the currents, and this was done by my supervisor. So yeah, this picture just to say that you can see the second class particles as void, and this just like help a bit like to see the model in a bit more symmetric way. So you just pick the void and the first class particle as the quantities to study, and you leave the second class particles. Okay. So how do the currents look like for this model? So you can like show that like using again this is by Cantini. By nested beta and zats, that okay, these currents like they have these forms. So these Z alpha and Z beta are some parameters that arise from a saddle point equation when you take the thermodynamic limit, and these like parameters are given by this equation. So for the moment, these are just like just parameters, but we'll see soon that they play more important role to understand, like to analyze the system. But yeah, for the moment, we just like they need to be taken within like within a domain. So this domain says so Z alpha has to be smaller than 1 and smaller than alpha, and Z beta has to be smaller than 1 and smaller than beta, and their sums has to be smaller than 1. So they belong to a domain of this form. And so now, if you again like write the conservation laws which correspond to this currents, then you have like a coupled conservation laws, and which are complicated. So this like I will not write the currents in terms of the density because simply the expressions are so long. But then if you it happens that these parameters that we just saw, these are the good parameters to diagonalize the system, in a sense that these are the Riemann variables at the end of the day. So basically, like if you write like the conservation laws in these like variables, then you don't have here like derivative of Z beta, and you don't have here derivative of Z alpha. But they don't completely decouple the system because the system is still coupled through the coefficients. Yeah. Anyway, like you don't need to care about this scary expression. Just like consider just a compact form. So you have some V alpha and V beta like that, which are the coupling coefficients. And so what's worth mentioning is that it's in order to understand the behavior of the system, it's important to study a bit like the mapping between the Riemann variables and the density. So this like so the density like domain belongs to just a triangle, and so for some conditions of alpha and beta, this mapping is regular. For other conditions, it has some singularities, and these singularities, they have physical meaning. Okay? So for instance, okay, here like if you take alpha plus beta bigger than 1 and alpha and beta smaller than 1 each, so you have everything is like regular. If you take alpha or beta bigger than 1, then you have like this segment here of the density, like it corresponds to a point in the Riemann variable in the Riemann space. This segment of here like as well correspond to a point, and then these are like singular points. And if you take alpha plus beta smaller than 1, then all of these segments on the diagonal correspond to a point in the Riemann domain.
Sorry, can you show the mapping again? Can you explain?
So basically, this mapping comes from the implicit from these like implicit relations. So I never wrote it explicitly because simply it's not worth it. It's just like comparison. So the best way is to see it just through the implicit form. Is it okay?
The invariant measure is always product?
Sorry, no, the measure is not the invariant measure. I mean, if it was product, then the currents would just be mean field, right? So the currents here are not mean field because the measure is not a product.
You know the invariant measure.
So we know the invariant measure in the ground ensemble canonical ground ensemble, and but that was done by another paper by Patrick Ferrari, Sazamoto, and Schbon. Yeah. So yeah, it's the invariant measure is as well known. Okay, so we're looking at the mapping. So now how to solve the conservation laws. So simply, okay, you know that like they might have shock solutions, so you need to consider them in a weak form, like to see the functions as some distribution acting on Schwarz space, or simply like in an integral form. So okay, if you do that, then concretely, that means that you can allow just for discontinuity in the solution, except that each time you have discontinuity, you need to apply the Rankine-Hugoniot condition, okay, which is given by...
The system is strictly hyperbolic?
It's not. It's almost strictly. It's not strictly hyperbolic. It has one point where with no, which has non-hyperbolic, which is where that was the two characteristics bit equal. So this like I can show you when at the right moment where I can comment on this where. Okay. So. Each time you have a discontinuity, you apply. You ask this continuous point to abide by Rankine-Hugoniot condition. But if you just stop here, then you have too many solutions. You don't even have unicity, and then you need like additional condition, which is the entropy criteria. And then if you do this both, now you can limit the weak solution into the physical solution by adding this entropy criteria, which basically like is physically it just means that you want your solutions to be stable under perturbation. It's one interpretation of it, but there are among other interpretations of the entropy criteria. Okay, so now taking into all of this into consideration, the simplest way to characterize, like let's say, the shocks are in the Riemann variable. So you just have two types of shocks, which are let's say if you fix the left boundary. And then you can just increase the Riemann the Z beta Riemann variable Z beta keeping Z alpha constant, or the other type of shock you can decrease Z alpha keeping Z beta constant. So this maybe you can call it beta shock, and this is called alpha shock. So now there are other types of solutions which are the continuous solutions. So these are like the refraction fans, and for these like types of solutions, the easiest way is to solve the Riemann problem, which means that like you start with the initial condition, which is just like discontinuity, which is uniform everywhere except a discontinuity at the origin. And what's special about this initial condition that it allows the whole system to be self-similar, which means that now there is only one variable which is x over t, and if you write the equations in terms of x over t, then you have like these equations which are quite trivial. So like in order for them both to be zero, so you either like z alpha has to be constant and z beta is given by this implicit relation, or the other way around. Let's say z beta is constant and z alpha is given by this implicit. And then if you write on the Riemann space, then you can. This would be two arrows, like one arrow going down, which means that if you are starting by left like Riemann variables, and left for Riemann variables and right Riemann variables which have the same alpha, z alpha, then you just decrease z beta continuously, and that would create a refraction fan, which we can call it beta fan. So of course, like in the density space, that would be two refraction fan. Okay? Well, then you can say the same as well. You can keep z beta constant and increase the z alpha. Okay, but here like you can remark something not usual, which is that these refraction curves and shock curves, they coincide. So it's in both cases just like, let's say, either horizontal line or vertical line in the Riemann space, which is special case in conservation laws. This is like so this model belongs to the Temple class model. So this special case is known as the Temple class model. And yeah, for me this is like maybe the most fascinating thing about this model, because it makes some it's an example where you can link like hydrodynamic integrability with microscopic integrability. So there is a link, and probably this model is a way to study this link. And the other, yeah. So for instance, like just like knowing that it was Temple class, I was able to find the currents just from the single species TASEP without even using algebraic nested beta ansatz. Okay, so now having all of these arrows, so now you can travel in the Riemann space or density space. So for instance, if your left condition is like here and your right condition here, you just like use these two arrows and you arrive to your destination. Okay, what if you don't have a space? Then there is a third type of refraction fan that goes along the boundary, which is this green one, and along the boundary we don't have second class particles. So this refraction fan is just TASEP like. So this is the same as the TASEP refraction fan. While the other ones are other, like these are refraction fans that they are not like linear. They have complex or at least like lengthy formula that I don't write because there's no point of writing. But yeah, in the Riemann variables things are much easier. For instance, if you want just to ask any question, it's almost always easier in terms of this variable. For instance, like here, the condition of the existence of this like depletion zone. So this zone where there is no second class particle. It's just this. So if you write it if you want to write it in the densities, then the formula will not fit in the slide. Okay, so now like from any point you can reach, let's say from left, you can reach any point on the right using the arrows, and then you can show, yeah, you can, if you want like to draw this like these shocks and refraction fans. So you can either have, so in general, you can either have like two, so the general solution is that you can have either two refraction fans of two different types, or a refraction fan then a shock, or two shocks, or a shock and then a refraction fan. Or like a refraction fan from of type like beta, then TASEP like refraction fan, then alpha type refraction fan. So then we did just some numerics just to verify that these are the things like coincide with the theory. So because basically like we just used the conservation laws with this current, we didn't really prove that this should work. And this is a model where it's not given for free that this can work, because this doesn't belong to class of model where you know that, like, let's say it's not attractive. I mean, it's not even. We don't know even how to define the attractiveness, but and yeah, for this model who are not like don't have invariant measure and are not attractive, then you don't know what is like in general if the hydrodynamic approach should work. So here it seems numerically that it works perfectly. So probably it's worth like proving it rigorously. Okay, so now we'll just comment on what happens on the boundary of this like density region. So because we saw that like I said that these singularities they have physical meaning. For instance, like in this, like when alpha plus beta is smaller than 1, so this like segment is singular, which means that it will correspond like to a cut in the TASEP expression of current, which is just hyperbolic. So now. So what does mean this like what does mean when we are here on the boundary? It means just we have a system with infinitesimal density of second class particle. Okay, so it means that this like in this regime, in the infinitesimal number of second class particles is not the same as the strict absence. So they have an effect, and this effect is that they cut this current here, which means like that. They will do a perturbation in the refraction fan. So let's say if you draw the refraction fan with this, just TASEP with this infinitesimal second class particle, then you have this big important perturbation. And it happens that this happens here, that for this situation, that this perturbation is for infinitesimal density is the same as the perturbation of a single defect put like in the origin. Okay. So, but yeah, so which is very curious, okay, or maybe not curious, but it's an observation. Okay, so now let's like go again to this, like let's say what happens if we put just a single defect in the origin. So you can, in general, you have like two regime. Like let's say when alpha plus beta is smaller than 1, then as we saw just before, then there is like a perturbation. This defect, like will perturb the system. You can just imagine if you can just put alpha and beta is 0, then nothing moves. This defect will not let anyone move, and it will will not move itself. So of course we create a perturbation. So yeah, but then if alpha plus beta is bigger than 1, then there is no perturbation, and then we saw that that mapping was regular. But this defect doesn't have any more deterministic asymptotic speed. So now the question becomes, how does now the profile is not anymore a question, but then the question will become how does this defect behave? Okay. Okay, so how to understand both of them? So each situation has different method to understand. So the first one, you just to understand what happens in the first method, you just you can just solve the Berger equation with you just solve the Berger equations with the interior moving boundary condition, because basically if you have just one defect with let's say uniform distribution, then we know what happens. We know how does the defect behave according to the surrounding density field. So this is known by Derrida and Malik. So now you can just solve it. So you can sometimes find that there is a perturbation, as we just said. Sometimes this defect will create one shock which is outside the refraction fan. Sometimes it will create two shocks. Okay, and then you can compare as well these with the case of the infinitesimal density of second class particle, and sometimes they coincide in some regimes and sometimes they don't, and this is still we don't understand exactly why do they don't agree all the time, or why do they agree more precisely. Okay, how about if this single defect, if alpha plus beta is bigger than 1, then basically this defect doesn't have deterministic behavior. The asymptotic speed doesn't have deterministic behavior. So, but still, it's possible to let's say if alpha is bigger than 1, then or beta is bigger than 1, then some of these particle will escape the refraction fan. So these are, and this escaping probability you can find it by mapping the situation and the distance between this particle and the following one with a random walker with absorbing boundary condition. But what is the distribution with particles who don't escape? This we don't know in general, except for some regime. Let's say if alpha and beta is smaller than 1, and their sum is bigger than 1, then we know that this actual distribution is uniform, and then this can be shown by mapping this situation into a profile with second class particle of density of rates 1, 1, and 1, but with the initial profile which is given by beta and 1 minus alpha. Okay, and this situation we know that it's uniform. But if you go out of this domain, then we don't know what is and in general it's not uniform. I mean, this is by simulation you can see that. So what can you do with this model? Okay, you can use it as a toy model to study multi-component driven diffusive system. So this is this is work we already did it with my supervisor, and we characterize the steady state behavior, the steady state density and the boundaries. You can use it as well as a toy model to understand these temporary class systems and the relationship with the hyperbolic conservation laws. Of course, somebody needs to prove the hydrodynamic limits. And there's still some other question about this, distribution of defect. But as well, the most general would be as well, let's say, to put to do uniform uniform profile and to do some small perturbation and to understand how does this coupled KBZ equation behave exactly. Thank you.
Time for questions.
You mentioned the point where the two characteristics have the same speed. Did you look at this point?
Yes. So it's I don't know if I have anything here to show about this point. No, I don't have any image. But basically, there is I mean I don't have any image. But there is only in the density space there is only one point which is located here, half basically. It's the point where the two densities are half. And here, yeah, in this, if you just like at this point on the boundary, it's located here. There, yeah, the two characteristic speeds like are equal, but everywhere else they are not.
When the two densities are 1/2, that means the third particle is not there. No?
Yes, exactly. It's exactly. There's like yes, yes. It means that either you have like either it's not there or you have like an infinitesimal density, because this model is not continuous on the boundary. So it means like with the infinitesimal density is not the same as non in general, depending on again on the alpha and beta.
The temper class. There is a paper by Baritot and Valco to prove the dynamic limit to conserve the two conserved quantities. There is any relation with the.
So I'm not sure. I mean, I know what is this paper. So yeah, again, they prove it for any temper class model.
Yes, it's
okay.
a different dynamic. It's in the temper class model.
Okay, it's another model in the temper class, but
yes.
okay. Yeah, it will be interesting to look. Maybe the same approach can be applied here. I mean, yeah, I will maybe ask you for this some other reference.
Okay, if there are not other urgent questions, I think we should move for lunch. And before that, let's thank Ali and